Thanks for coming. It is a pleasure to introduce today our Severo Ochoa speaker, Dr. Leticia Carigi. She's a senior research at Instituto of Astronomy at la Universidad Nacional Autónoma de México. She is also head of the astronomy postgraduate studies for the Institute of Astronomy. And she is also Secretary General of the Mexican Astrobiology Society, and she has been awarded with with several excellent prizes in Mexico. Her main subject of research are cosmochemistry in local group galaxies and astrobiology at galactic scales. In her PhD degree thesis, she focuses on the development of a software for modeling the chemical evolution in the solar neighborhood. And since then, she has extended improved her code for modeling chemical evolution in different types of galaxies. This code has been very useful for international research community. And she has been, or is currently, advisor of 12 master thesis or doctorate thesis. And she's visiting us as Severo Ochoa, professor, to work in the project Chemical Evolution of Dwarf Galaxies. And she will be here until January 4. And she's a very well-known research at IEC with several collaborators among us. So thank you for coming and welcome to this, your second house.
Thank you very much. Thank you, Sebastian, for this kind presentation, and thank you for coming in this raining day with a problem with the schools and kids and several things. Okay. Well, I am going to talk about a compilation of 2 or 3 chemical evolution models of the spiral galaxies in the local group in order to obtain correlation between the galactic mass and other properties in these galaxies, in M33, M31, and in the spiral in the Milky Way. These chemical evolution models were built with several people, with a cosmochemical group, and some of the members of these teams at the UNAM is Fátima Robles, Manuel Peimbert, Nancy Ávila, y Regis Durazo. Regis Durazo is, I don't know, the last week were here. And here in the Instituto de Astronomía de Canarias, de Astrofísica de Canarias, the members are César Esteban, Jorge García, and recently Sebastián Hidalgo. Okay. First of all, I would like to show you what is the importance of the chemical evolution models and to build solid chemical evolution model based on reliable abundances, chemical abundances, and data. For example, okay, the chemical evolutions models are useful to infer galactic history formation, how a galaxy formed by accretion. Star formation history, how the star is stellar form, the initial mass function, obviously the stellar properties like the efficiency of the star to produce new elements, new chemical elements, and when a chemical evolution is built to reproduce at least 3 observational constraints. The first one is the radial distribution of the total baryonic mass. The second is the radial distribution of the gas mass. And the third is the abundances of at least one chemical element. In this case, I prefer to work with oxygen because it's the most important chemical element among the heavy elements. And it's one of it's easier to determine the oxygen abundances in A2 regions, for example. And then these chemical evolution models then are tested with other observational constraints, like other chemical gradients, star formation rates, and other things. Therefore, if we have more precise observational constraints, observational data, we can build solid chemical evolution models and infer better properties, better histories, chemical histories for this galaxy. Okay, here you can see the picture of the local group. And first, I am going to talk about M33 of the triangulus galaxies. Why? Because this galaxy is a very special galaxy, because it's in the medium side. He has a medium side. And as I told you, it's very important to have a set of the observational data. So a good, better observational data. Therefore, the first one is this picture is, I show you the profile of different. I have a problem. Let me see. I prefer this one. I feel like gravity with this. Okay. I am happy. Well, the black points represent the radial distribution of the gas mass in M33. Here we base that distribution on the high atomic and molecular gas mass by Gratton and collaborators, and then we correct this hydrogen distribution by the contribution of helium and heavy metals. Therefore, the mass gas, including the helium and metallicity, is more or less 1.3 times hydrogen mass. This is very important that in the outer part of the galaxies, for galactic radius higher than 6 kiloparsecs, M33% increase of the gas mass. That is very important, and this is a new data. This is updated. Thanks to this data, we found an important result. Then the red triangles represent the mass star, the radial distribution of mass stars, and we add the living stars and the dead stars, the remnant, like the black holes and everything. Therefore, the stellar mass is more or less similar to the living stars. And the total mass, the total baryonic mass has present a double exponential profile for I have a problem here, for galactic radius less than 6 kiloparsecs, sorry. The baryonic mass follows the behavior of the stellar mass, but for the external part, the outer part of the galaxies, the baryonic mass follow the behavior of the gas mass. Therefore, the baryonic mass presents a double exponential profile. That is not very common in spiral galaxies. Well, and the other is very important here, for example, for Cesar and collaborators and Artemio. I'm so sorry, Artemio is not here. But here we collect chemical abundances of oxygen for different H2 regions and stellar and or B stars. For example, the magenta stars represent the stellar abundances, chemical abundances from O and B star by Urbaneja and collaborators. And I remember among the collaborators is Artemio. The 2 points over there. Okay. This is the oxygen abundances determined from recombination lines by Esteban, and the rest of the symbols are oxygen abundances from collisional excitation lines or different others. You can see that the stellar abundances is the values, the oxygen values from OB star is similar to the oxygen abundances from the combination lines, but is higher than the oxygen abundances from collisional excited lines. That is a really important problem here, because the model is built to reproduce this one. It is built to reproduce a gradient. But you can see a big spread, and really, I don't know, is probably to mention that here we have a gradient. So when we correct the data, for example, the gaseous values, the oxygen gaseous values determined from collisional excitation lines, we increase this data by 0.23 dex due to the effect of temperature. Okay, and that is the common the T square, the factor T square factor, and in both cases for cell gaseous abundances and recombination lines, we introduce also the correction by dose depletion. And when we correct the gaseous abundances, in this case, the corrected gaseous abundances is similar to the oxygen from O and B stars. This is very important because in the area here is continue the discussion what is the best way to determine abundance from collisional recombination line or collisional excitation lines, and it depends basic about the physics in the atomic physics. No? For that reason, we prefer correct in order to have a consistent data. And we have more or less gradients, and the model will try to reproduce this gradient. Okay, so what is the chemical evolution models for M33 for variation, and mainly the ingredients of a chemical evolution model? First, we need to form a galaxy. That means that the galaxy is formed according the semi-analytical models, the cosmological models. The galaxies, the spiral galaxy forms according an inside-out scenario. That means the inner part of a spiral galaxy forms quickly and early than the outer the outer part of the galaxy. And this galactic formation have to reproduce the total baryonic mass, the radial distribution of the total baryonic mass. For that reason, in this case, the inner part or the galaxy is formed like inside-out scenario, slowly but inside, and the outer part is more or less uniform. It depends. Is due to the double exponential behavior of the total mass. When the gas is in the galaxy, the star formation starts, and we choose the star formation, the chemical Smith law, and one of the free parameters of the model is the star formation efficiency. And this star formation, the values of this star formation, is obtained to match the radial distribution of gas mass. The star form according to mass distribution in this case by Krupa. The IMF by Krupa is steeper for massive stars than Salpeter IMF, and we prefer this steeper IMF because we test this IMF in the cosmochemical laboratory, that is the solar vicinity and our galaxy, the Milky Way. With this initial mass function, the model of the star formation, the model of the chemical model in the solar vicinity reproduce better the constraints. For that reason, we prefer that initial mass function. And then the upper mass of this initial mass function is also a free parameter of the model, and like oxygen is produced mainly by massive stars, the upper mass of the initial mass function is obtained to reproduce to match the absolute value of the oxygen gradient. In this case, is more or less 50 solar mass. And the main ingredient of this soup is the yield, the stellar yield. We work with stellar yield dependent on the metallicity for low intermediate mass stars, massive stars, and supernova 1A. We do not consider radial flows of gases or stars, or loss of gas from the galaxy to the intergalactic medium. Sorry. I can hear you.
Okay. It's about the infrared law that you are using. Could you try to explain us where does it come from?
The infrared?
Yeah.
Okay, the first one. Okay, do you remember? Let me... Okay. Here, this is the radial distribution of the total mass, something like this. You have here a double exponential behavior, okay? Oh, okay. What is the total? The galactic formation gives you the amount of gas and stars in each ring, and therefore the infrared need to reproduce this double exponential behavior. what is exponential.
Yeah, so you use that law to reproduce the mass distribution
Yes.
Of the galaxy. So somehow that is connected with the assumption number 5 that there are no radial flows. So if you would allow for radial inflows, you might have to change your inflow law. Is that correct?
Yeah, the point is this galactic formation is the inflow occurred directly in each rings. And you don't have, in my code, you don't have movement of stars or gas through the disk. It's consistent.
Okay.
The point is, the second point, I don't know if your doubt is the second point, we don't have fontaines, galactic fontaines, when you lose the gas and the chemical element from the disk to the halo.
Neither you have radial inflows. So what I'm saying is that if you relax number 5, I mean, if you, I don't know whether you, I mean, I think you cannot do in your model, okay? But if you were able to relax the hypothesis number 5, allowing for radial inflows, then you might have to change the inflow rate that you are assuming,
yes.
Okay?
If I change the number 5, I need to change the number 1,
okay.
Of course. Thank you. Okay, result of the chemical evolution. First of all, here, one of the 3 parameters is the star formation efficiency. This star formation efficiency is obtained to reproduce the gas mass distributions like this. And first of all, we try with a constant value in the space and in time. With this value, we can reproduce the behavior of mass gas, star formation rate, and stellar mass in the inner part of this galaxy of M31. Also, we can reproduce the gradient, the oxygen values in the inner part in M33. But the point, the problem here is that we cannot reproduce the outer part in anything, the mass gas, the star formation rate, and stellar mass. And that here is very important because for R higher than 6 kiloparsecs, really, we have a lack of data. We have more or less 2 or 3 stellar abundances and 2 or 3 gaseous abundances with a big error. So it's very important to have observational, to have oxygen determinations in this part of the galaxy. I think Cesar told me something about the future data in this area, and that is very, very important to discriminate between models and to discriminate how the external part of the galaxy, of this galaxy, is formed. This is not solar neighborhood. This is M33.
No. I mean, what is the reference, the corresponding reference for the solar neighborhood?
I don't remember.
So for the solar?
I don't remember. Let me see. Okay, let me see, yeah.
Usually solar is about 1.
Solar neighborhood for you. Solar neighborhood for you. Solar neighborhood here is 0.5. Well, so we need to change something in the model to match, to reproduce the outer part of this. And the point is the efficiency of the star formation. We change the efficiency of the star formation in the outer part of the disk, and we reproduce the gas mass, the star formation rate, the stellar mass, but in this case, the gradients, the slope of the gradient, really steeper, is steeper than the previous one. Now, again, it's very important to have oxygen determination in this part to discriminate between the previous model and this model. Well, how we change the efficiency, the star formation efficiency in the outer part? Here, I show you the star formation, the history of the star formation rate for 4 galactic radius. For example, here the peak, here the first peak is the formation of the halo formed in 1 gigayear, and here is for 9 kiloparsec. The star formation is from, for example, the star formation of the Higgs is from 1 kiloparsec until 1 gigayear until 6 gigayear, and they cut. The star formation decrease almost to 0. After, for example, for 7 kiloparsec, the star formation decrease later, more or less at 9 gigayear. Therefore, the decrease in star formation efficiency with the galactic radial is early and higher early. This is the effect of maybe of RAB affecting the disk due to interaction with other galaxies. This is very common. This is an effect also in protoplanetary disk. Also, we have this effect. So, in this case, we found an outside in stellar formation in a spiral galaxy. This is important to distinguish between the stellar formation and the galactic formation. Here, do you remember, I don't know, if the galaxy formed according inside-out scenario, the gas accreted according this gas, but the star formation history is different in the outer part. This star formation follow the outside in a scenario. What means this? For example, if we study the average stellar age in the outer ring at 9 kiloparsec, more or less, is dominated by all population. But in the central part, more or less in 6 kiloparsec, the population is dominated by the stellar population dominated by young stars, and this means the inside-out scenario for the star formation, not for galactic formation. So, the mean stellar age increased with the radius. What happened with the inside part of the disk in the same galaxy in M33 is inside-out formation, is opposite. The inner part, for example, this is the star formation rate versus time for 2 kiloparsec. Is dominated by all the stars, and for 6 kiloparsec is dominated by younger stars. So this is a star formation inside out. So in the same galaxy, we have 2 scenarios for inside, for a star formation rate. Inside and outside, inside out and outside in. Let me see. Okay.
I'm lost. So, sorry, I don't know if I am the only one who is lost. Then these lines of different colors.
This picture.
Yeah, these lines of different colors, what are they? Come from the model of Sanchez-Blázquez? Yeah?
No,
No?
modeling from the chemical evolution models. The chemical evolution model, to reproduce the increase of the gas mass in the outer radius and the decrease of the star formation rate in the outer radius and everything. Let me check. Okay, to reproduce this part, the star formation rate, the model need to change the star formation rate, to reduce the star formation rate. How to reduce the star formation rate? Then we try to reproduce for each radius the specific gas mass, the stellar formation rate, So the model inferred this star formation history for the outer part to reproduce the gas mass, the stellar formation, blah, 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 blah.
So each line is for a different radius? Each color?
Yes, a different radius. For example, for the blue one is for 9 kiloparsec, the external one.
For the radius, for a ring, around 9.
8 kiloparsecs, 7 kiloparsecs, as I said, inference of the model. And I mentioned Sanchez-Blázquez et al. Because they have a numerical model, blah, 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 and they found more or less the same behavior for the outer part of the galaxy due to interaction with other galaxies. The chemical history has a very good memory, and for that reason, we could found this behavior outside in the stellar formation, but the galactic formation was inside out. It's okay? More or less. Okay. Now I am going to talk quickly about the Milky Way. Why? Because we need to try, we would like to connect the smaller spiral galaxy in the local group that is M33 with the Milky Way and the M51. Here, I already showed you the picture when you asked me. And here is the Milky Way. This is a work with a paper by Esteban and collaborator of this year. I think he had two collaborators. And the model was built to reproduce the gas mass distribution and this oxygen gradient. This oxygen gradient in this paper, Esteban and collaborator determined the oxygen abundance of this H2 region. What is the name of the H2 region? AGC? And with this oxygen determination, the gradient has a flat behavior in the outer part. It's very common now for the spiral galaxy. The outer part of the chemical gradient in some spiral galaxies are flat. And with this beautiful and wonderful work, we found this flattening in the gradient in our galaxy using a consistent data. This point is oxygen abundance from recombination lines and corrected by dust depletion. The star formation rate is reproduced with this model, and here I present the star formation history of the Milky Way for 4 kiloparsec, for example, and 16 kiloparsec in the side out. And you can see easily that in the Milky Way, the star formation history follow an inside-out scenario like the galactic formation. M31 is the biggest galaxy of our local group. Here, we reproduce again the gas mass, and we obtain this gradient. You can see that the dispersion is very big. We have a few points because M31 is very difficult to determine abundances due to the bright of the H2 regions, more or less, because it's more metallic. So to reproduce this, the decreasing of the gas mass distribution in the outer part, the model needs to increase the efficiency of the star formation rate, and for that reason, the model predicts a flattening in the outer part, similar to a Milky Way. This is a paper that is now with the referee, and we hope that the next year will be accepted. And how is the star formation rate, the star formation history for the M31? And easily you can see that, again, in the inner part, the stellar population is older than the outer part, and therefore we have here an inside-out stellar formation again. So the inner part of M33, the smallest galaxy in the local group, the inner part, behave like M31 and Milky Way, the biggest galaxy of the local group. What about the external part? How we compare the outer path of M33 with other galaxies of the local group? And for that reason, I am here to work with the group of stellar population. This group here is a result of this group. It's a paper of this year by Hidalgo and collaborators. And I present only the star formation rate, the star formation history normalized for 4 dwarf galaxies, 2 dwarf spheroidals and 2 dwarf transitions. And the name is Cetus, Tucana, LTCC3, and Phoenix. This is the star formation rate, normalized star formation rate versus time for the inner radius for each galaxy and the outer radius for each galaxy. So you can see the star formation rate decrease earlier in the outer part and in more or less 6 years ago in the inner part. Again, here in the smaller galaxies of the local group, Hidalgo et al. Predicted an outside-in stellar formation in this galaxy. Similar what we found by chemical evolution models in the stellar part of M33. Therefore, the stellar part of the M33C, behaves similar to the dwarf galaxies of the local group. And I think this is the most important conclusion of this work. Is M33 is a galaxy with an intermediate galactic mass, and present characteristics similar to the biggest and the smallest galaxies in the local group, and is the unique galaxies with this galactic mass, the unique galaxies in the local group, and maybe connect the formation and the evolution of both type of galaxies, the biggest and the smallest. For that reason, it's very important to study M33 in the inside and outside parts of the galaxy. Conclusions. First of all, for people who work determine oxygen abundance, is very important. The oxygen from OB star is similar to the oxygen from H2 region if and only if the abundance is determined by collisional excitation lines is corrected by effect of temperature effects in the gas, and those correction and the oxygen abundances from H2 region and from recombination lines needs only a dose correction. The biggest spiral galaxy, like M31 and our galaxy, form stars according an inside-out scenario, following the galactic formation scenario. Dwarf galaxy form stars according an outside-in scenario, and really we don't know how they form. One is of my work in the future, near future. M33 is a medium galaxy and form star according to both scenario and depend on the mass regimes. In the inside of the galaxies, the mass is bigger and behave like the bigger galaxies, and the south, the mass is lower and behaves like a smaller galaxy. And the star formation do not follow the galactic formation history. Observational data, chemistry, mass, gas mass, stellar mass, star formation rate, everything is crucial, is essential, is required to improve the model, the chemical evolution of this galaxy. Therefore, we have a work in progress. And first is we need reliable chemical evolution models. Okay. My computer hates the propaganda. How do you say propaganda? My students are working in chemical evolution models. It's a Mac, sorry. Yes. Okay, my student is working in several chemical evolutions. Using the same code, the same chemical evolution code that is very important, with similar ingredients to obtain consistent models. And the idea of the third papers of Fatima, my PhD students, is to correlate the gas mass, the galactic mass of these three spiral galaxies with properties of the galaxy. For example, oxygen gradient, the slope, the absolute values, flattening or not flattening, the galactic formation efficiency, the star formation efficiency, if the star formation follow the galactic formation, and when follows, or what is the minimum baryonic mass for an inside-out or outside-out scenario, etc., etc., etc. And that is all.
Okay, thank you very much for these nice results. We have time for questions.
Nice talk. Well, what happens if the recombination line abundances in the outer part of M33 are consistent with the constant star formation rate model?
Yes, but the point is, really, we don't have a lot of information, chemical information, in the outer part of M33, and we don't have abundances from recombination line, only by collisional exciting line. This one, something like this. Two points represent stellar abundances from O and B stars, and is from collisional exciting line.
Yeah, but in the other forward, that one.
You have the problem.
That one. If in the outer part the abundances would be
lower than...
Lower, no. If they're lower, you have the solution. But if they are higher, do you have any explanation for that?
Life is hard. Life is hard. Yeah. Okay, we have problems in this case. Maybe the variation of the star formation efficiency change, but we don't know. After you determine that oxygen, I think.
I wonder how the conclusions about this inside out or outside in growing depend on the underlying assumptions of your chemical evolution model. This is a stationary model, basically, where star formation rates are stationary, are constant with time, and you don't allow for stellar migration, you don't allow for gas inflow, radial migration of gas, and so on and so forth. But this is something that looks a little bit artificial if you think about the numerical models of galaxy formation, where the formation of a galaxy is something that is everything but stationary. Okay, you have clumps of gas that are very irregular, hit the disks, and they are forming little by little. So I wonder how your conclusions depend on this underlying assumption, whether you can make a comment on that.
So what my conclusion is?
Whether the conclusions depends on these underlying assumptions. The fact that it's growing, it grows inside out or outside in, depend on these assumptions, which seems to be critical. For instance, in M33, you have this flattened, you have this growth of mass in the outer parts, at the same time this drop of metallicity, which you, explain as this outside in growing of the stellar population. But it might be just due to, the inflow is not stationary, so you don't have gas on the outer parts, and all of a sudden you have a clump of gas that form the outer parts of the disk and this metal pool, and that explains the same thing in a different way. So I wonder how the underlying assumptions affect your conclusions.
Okay. First of all, the increasing of the gas mass in the outer part is observed in the azimuthally in the galaxy. It's not in one part of the galaxy. So merger, for example, for a satellite or a big molecular cloud or something like this is really we don't know. We don't think that is the cause of the increasing of the gas mass. If we assume a second inflow, something like this, it's very difficult to explain that in present time, in the intergalactic medium, there is a big molecular gas, atomic gas with a primordial metallicity, for example. If you need to change the info, something like this. So, really, I don't know what is the I think that is a good solution based on the ingredients, based on the assumption of the model. But also, if we introduce radial migration, stellar migration, or gaseous migration, or something like this, the results will change. Okay. But really, I don't believe in the stellar migration. I think the stellar migration is important, but not is the panacea. For the fact is every spiral galaxy showed a gradient. If the stellar migration was very, very important, the gradient will be flat, more or less.
Well, a comment. I wanted to mention that I'm sure you are aware of this, but you haven't mentioned that direct results on the star formation history of this galaxy really are in agreement with these conclusions. There is a work by Williams et al. In which I don't remember exactly the exact radius in which this happened, but it's something like this. At least qualitatively, it agrees that inside-out formation, star formation history is found for the inner part, and then the same scenario as you are describing. Then for the case of the LMC, which is a somewhat similar galaxy, is just slightly smaller than this one. Maybe it has half the total mass, something like this. We find something like, well, we don't know about the very inner part, but we do find an outside-in star formation history from 3 kiloparsecs outwards. Oh. Directly from color magnitude diagrams and from computation of star formation histories. Mm-hmm. So similar to the results that you have shown from Phoenix, Tucana, LGS3. So I think there is information that is very direct information from the color magnitude diagram from which you can compute the star formation history directly, and it totally agrees with your conclusions.
Thank you.
To what extent could an outside-in model or scenario be mimicked by a model in which you have rather uniform formation in the whole disk, followed by increasing formation in the center, so that your mean methodicity, your mean stellar population and energy distribution is younger in the center, but nevertheless the whole disk formed earlier, but the center disguises this to some degree, and I don't know what you would think about that.
Do you talking about the dwarf galaxies?
In any circumstance, and either of these, any galaxy which looks as if it's just doing outside in, which it is in a way, but if you had almost uniform star formation, so you have an underlying older population, which is disguised by the newer population in the middle. So it isn't exactly outside in. It's kind of uniform and then in, as it were.
But if you have a uniform star formation rate, I don't know how I can explain the gradients, for example.
Well, you can explain it because it's disguised by what I'm saying. I mean, the older population is less luminous, and therefore the younger population where it dominates, and you don't see the older population. And there are often controversies about whether there are underlying older populations in galaxies, to what extent these can be hidden by the luminosity of the younger population, not just in photometry, but also even in abundances and so on. Okay.
My dear?
Yeah.
You assume underlying old population and only in the center a young population, a continuous. I mean, yes, in some. So to explain the smooth gradient that we observe in all dwarf galaxies, you need some kind of strong migration to migrate young star forming in the center to outside. And there is a few models, or Stinson, for example, that show that radial migration is really not important in dwarf galaxies. So I agree with you that will represent a kind of migration, but not a smooth, a kind of gradient in the age or metallicity. But what we saw in the dwarf galaxies is a smooth gradient. So that could be, it's difficult to match with that scenario.
Miguel.
Maybe you did now, but have you tried to reproduce the spread, the scatter that you find in the difference in the abundance for different radius?
No.
Okay.
No, and in M33, the 33 is a really dispersion. In M31, in the galaxy is different. The dispersion in the gradients is in the oxygen values is slow. But in M33, we have a real problem. We know the person who determined oxygen abundances, okay? And the point is maybe there is a smaller galaxy and maybe a stochastic effect and something like this. I know you very well. But I think it's a good project. Include a stochastic effect in M33, especially. Okay.
So, okay, we were discussing here. Okay, so then two questions then. One is, does it has to do with this galaxy, spirals, the anti-truncation, with bigger galaxies indeed, that this has been found?
Sorry, I didn't get
this,
it.
You know that there is anti-truncations. So in
anti-location?
Well, truncations and anti-truncation.
Anti-truncation, okay.
Okay. So do you think this has to do with that? Depends probably on the radius that it has.
I depend on the radius, and I think depend on the mass available to form stars during the history of the galaxies.
No, because there is, of course, here people in this house, they already have shown that there is sort of U profile in color as well. Mm-hmm. Okay, and it happens exactly in the anti-truncation. Okay, so this is something interesting to maybe to check. Yeah. And the second point is that it has to do maybe with the, whether it's inside out or out inside. Then it should be also reflected in the gradients of metallicity.
Yes.
Of course, you have to take into account the mass of the object.
Yes.
As well.
Yeah.
So probably you get a sort of smooth
gradient.
Yeah.
Here you can see, for instance, in this case, the flat gradient with the star formation is flat, and therefore the star formation continue the inside-out scenario. And the continuous line represent when the star formation is outside in, and for that reason it's very important to obtain the chemical data for this part of the galaxy. Yes? I fully agree with you. I fully agree with you. Yeah. The chemistry has a good memory, better than the photometric.
More questions? No. Okay, so just to remind that you can keep talking to Leticia right now at the coffee break and for the rest of the month, and you can find her in the Severo Ciao visitor office, which is on top of the cafeteria. So let's thank the speaker again, please.